All right.
From UIUC.
Yes. Thanks for the intro. I'll be talking about this, and don't worry if you don't know what all the terms mean. I will explain how MPC algorithms work and what embedded planar graphs are. And so this is joint work with Wei Zheng at NUS in Singapore. And just one interesting thing about this is this paper was that in this paper we're going to use graph drawing to design algorithms for planar graphs. Usually it's the other way around. Usually when you're trying to solve a graph drawing problem, which is about how do you draw a graph in the plane, you use planar graph algorithms to draw that graph in the plane. But we're going the other way, so that's a bit fun. And this work was presented at SOTA of this year. All right, now let's get started with the definitions. And let me just introduce the model of massively parallel computing. I assume everyone knows what a graph is, so I won't talk too much more about that. Right, actually, one more thing about graphs is we'll mostly be talking about planar graphs, so the number of vertices and the number of edges will be approximately the same. There'll be O of M would be O of N typically in our case. So let's talk a little bit about massively parallel computing. And this is just an alternative model of computation. Right? This is a parallel model of computation, and it's especially well suited to deal with large amounts of data. So if you consider these squares that I've drawn to be machines, we could have many of these machines, and each machine has some bounded amount of memory that I'll say is, say, order S for some parameter S. And these machines can all talk to each other, and the graph is going to be stored on these machines. And the important thing is that since this model is suited for dealing with massive amounts of data, there's going to be a gigantic graph that can't even fit on a single machine. Right? So the way we store the graph on our machines is each machine will store edges. And it'll also store, say, some identifier to identify which edge is which, or which vertex is which. Right? So maybe the edges have a label and the vertices have labels too. So every machine can only see one small part of the graph, and every machine can only store, say, order S number of edges, right? So to even store this entire graph, you would need something like M over S machines. And we're going to assume we have that many machines. Yeah?
Two vertices, they have different colors, right?
Yeah, so here I'm just using colors to denote the identifier of the vertices.
They have different colors, or it's the same color? Sorry.
Which two vertices?
The blue one, the blue ones.
One's purple.
There's a purple and a blue, but like the colors aren't, they should have different colors on the endpoints, but maybe my colors weren't.
So you should have like a distinct color for each different vertex.
For each different vertex, yeah, but they might be, these say might be the same vertex, but we're just storing a list of edges, right? Yeah, okay. Yeah, so we can assume that we have enough machines, like on the order of enough machines to store the entire graph, but we don't really want to use that many more machines, right? So we want to limit ourselves to, say, around M over S machines. And yeah, so in this model, the idea is that if you want to do some local computation, that's sort of cheap, because each machine can store all of this in its local memory and then do whatever it wants. The expensive part is actually communicating, transmitting information between the machines. So the way we model that is the communication will proceed in rounds. So in each round, the machines can all talk to each other, but they have limited bandwidth that they could send in a single round. So in a single round, they can transmit order S bits of information, since that's all that the receiving end can store. Right? And it can send that many bits of information to, that it can send out that many bits of information as well. We'll just say it that way. So yeah, so the goal is to minimize the number of rounds of communication we have here.
So that's for like total sent out or to each different machine?
So total sent out and received, but you can compute various primitives, like if you want to send one message to all the machines from one single machine, you could do that in like 2 rounds or something. Yeah, so our goal is to minimize the number of rounds, and we won't care too much about constants, so we'll just minimize the number of rounds up to some constant. And the question, we have to specify what question we're trying to solve. And so typically, we want to solve any question you want to ask about the graph. Say connectivity, how many connected components does this graph have? MST, like what is the cost of the MST, or to somehow output an MST. And you can output an MST might still be too big to fit on the machines, but you can output the MST by storing for each edge, is it in the MST or not, right? Just a single bit of information. You can also ask about single source shortest paths, min cuts, max flows, anything, things like this, right? These are natural questions to ask. Yeah, and the last thing I'll note is I'll define this fully scalable. So fully scalable, as you saw in the title, it just means that we're going to choose S to be particularly small. As in, it's going to be n to the delta for some small but fixed value of delta, so we can't even store all the vertices in a single machine. And if you want, you can think of delta to be like 0.1 throughout the talk or something. So, yeah. And so there is actually a well-known bottleneck called the 1 versus 2 cycle conjecture. So if you're given a graph that's stored in your machines like this, and you're working in this MPC model, and you want to determine, okay, is this graph an n vertex cycle, so 1 single cycle on n vertices, or 2 cycles on n over 2 vertices, right? Like if you only look at very local bits of information, the vertex is going to, all the vertices just have degree 2, right? So turns out, well, okay, there's this conjecture that if you have sublinear memory, so sublinear in the number of vertices, and I guess edges in this case, memory, you will need to use order log n many rounds. And of course, there is an algorithm that matches that. And so this is just for, say, connectivity, right? Like if you can't distinguish between n vertices, a cycle with n vertices, and 2 cycles with n over 2 vertices, you can't output how many connected components there are. And so all the other problems of MSTs, shortest paths, cuts, that's just strictly harder. So naturally, you can't do this. This conjecture says that, in this regime of sublinear memory, we can't really do things in less than log n rounds. But our paper will be about constant round, fully scalable algorithms.
What's
Yeah.
wrong with counting the edges to distinguish in these 2 cases?
Both graphs have the same number of edges, right?
Oh, it's wrong.
Yeah, so locally each machine will have some number of edges, but there'll be maybe, oh, I forgot to mention this. You can assume that the edges, say, are adversarially distributed or randomly distributed onto the machines. So you don't really have any information, like they aren't sorted by connected component already, right? Yeah. And if you wanted to, you could randomly sort or randomly shuffle the edges yourself. And also, you can even sort things in constant rounds in this model, but that's a aside. Yeah, are there any more questions about this? Okay, right. So in this paper, we'll talk about constant round fully scalable algorithms, and we'll talk about algorithms for exactly these problems, connectivity, MST, and so on. And the trick to get around this conjecture, because we will not be disproving it, is we're going to be working in embedded planar graphs. And what I mean by that, by embedded, is I mean we are given explicit coordinates on every endpoint, and we're also given, we're also told that the drawing of the graph in the plane, if you connect all the edges by connecting the explicit coordinates, you'll result in a straight line drawing such that no two edges cross. Right? If you want, you could generalize this a bit further, but this is, for simplicity, this is what I'll stick with. And yeah, so we'll be talking about this embedded planar graphs. And notice that this is, we need the word embedded here, right? Because if you look back at this n vertex versus n over 2 vertex cycle, like it's not enough that they're just planar. These cycles are planar graphs. So we really need this additional assumption of coordinates. And with that, like, so this graph, it's pretty easy to tell that there are two connected components. But this one on the same vertex set, it's not so easy, right? So just knowing the vertex positions is not enough. It's all about the edges. And do people see whether this is one or two connected components?
It's two.
Anyone think it's one?
It's like two in the left.
Okay, yes, it's two. They're pizza. Ah.
Not all heroes wear capes.
So repeat that. We assume that each vertex you're given the coordinates and the edges are straight lines.
Yes, you're given the coordinates, and the edges are straight lines between pairs of points. And if you just draw all of them in the plane, they won't induce any crossings. So it means that we're given some explicit embedding of a planar graph with coordinates. If people want to grab pizza, then maybe I can pause for now. Because I'd rather not give a talk in front of hungry people.
And don't stand between.
Yeah. Yeah, I was told never to stand between people and their lunch. All right, now that you got pizza, here's another graph. I changed some edges very slightly, and now is it one or two cycles? How many connected components are there? Yeah, it's hard to see. It's one. If you look between the two, I just swapped two edges in the middle there. And so, so it's actually not even completely obvious how you would solve the one versus two cycle conjecture, even if you're given this explicit embedded coordinates of the graph, because your embedding can look rather nasty and wonky with holes everywhere and all that. But nonetheless, this is possible. And this was actually first done by Holm and Tětek in SOTA of 2023. And so what they showed was that if the total amount of space you have is linear, and you had at least n to the 2/3 memory per machine, plus a little bit more, you could actually accomplish this. Right, so this already breaks the 1 versus 2 cycle conjecture. Our contribution is that we bring the memory requirement all the way down to any polynomial, any small polynomial in n, so n to the delta for any delta bigger than 0.
I don't understand. The result is that they can do the MST in a constant number of rounds?
Yeah, so, yeah, sorry. All of the results here are constant rounds. So everything is constant rounds, but they need at least n to the 2/3 memory per machine in their original paper. And we refine this and reduce it all the way down to n to the delta. Yeah, so everything here is constant round.
And correspondingly, you need more machines, right?
Yeah, I mean, you need more machines just to store the entire graph. Yeah, so I've written total space, but the number of machines is going to be the total space divided by the space per machine. Right? Yeah. Okay.
Do we know that in the extreme case where you had like constant or logarithmic memory per machine?
Yeah, so if you have logarithmic memory per machine, this is, I think, this should be equivalent to like the PRAM model of computation, which people have studied a lot in the 80s and 90s. And they're doing anything in less than log n rounds is, like you can't even, there's a lot you can't do. Like you can't sort things in less than log n rounds, so you don't really expect to be able to solve harder problems in constant rounds. But yeah. Right, okay. We also have a slight refinement of their single source shortest paths to improving their constant approximation to a 1 plus epsilon approximation. Okay. And we also show that we can do cut and flow based problems because we can, because in planar graphs, it amounts to doing something in the dual, and we can do something in the dual, and I'll get a little bit into the specifics of what we're doing there. We can also solve some problems outside of planar graphs, like 2D Euclidean MST. And in Euclidean MST, in that problem, you're given a set of points in the plane, and then you just want the minimum spanning tree that connects all the points. Maybe it looks like this. If you have another point, maybe the MST looks like this, right? And this problem is actually reducible to just MST in a planar graph, because you could take the Delaunay triangulation of the points. So if you had a good algorithm for, so it's known how to compute the Delaunay triangulation in constant rounds. So if you know how to compute the MST of a planar graph with a fixed embedding, which you do when you have a set of points, then you can also compute the 2D Euclidean MST. And so we also improve the memory requirement down to n to the delta. And you can also solve problems with edit distance. So you can solve, we present 1 plus epsilon approximate weighted edit distance that matches the best prior known bound for 1 plus epsilon. There's also, if you're familiar with edit distance, there were some results about subquadratic time 3 approximations or so, but none of those work in the weighted setting. So our result is still interesting there. And this is because edit distance is, you can think of it as a graph problem of some sort. If you look at the dynamic programming formulation, it's about paths in some grid graph with diagonals, and this is itself a planar graph, right? All right. And so, yeah. So now I'll start and get a little bit into how we achieve these results, because I think they're quite cool. And as a warm-up, we'll talk about planar separators. So if you're given a planar graph like you see here, a planar separator there's a planar separator theorem due to Lipton and Tarjan in the 90s that says that there's a set of square root n edges where if you rip them out of the graph, the remaining pieces of the graph will have components of size at most 2/3 n. So it's a very small number of edges, root n, and if you remove them, you get smaller components. And there's a generalization of this to what are usually called R divisions, but here, for notation reasons, I'll call them S divisions. So if you repeatedly apply the planar separator theorem, you can get a set of, say, n over root s edges that separates the graph into pieces of size at most s. And each component has a very small number of boundary edges, only square root s. So you can choose this parameter s however you like. And if you choose the parameter s to be exactly, n to the 2/3, you'll get the planar separator theorem, but you can choose s to be much smaller, right? Like n to the delta or something.
Wait. You get s is n to the 2/3. Why does it recover?
Sorry, not s, n to the 2/3. 2/3 n.
Oh, okay.
That's what I meant. Yeah, because you want size at most 2/3 n. Right. At most s, yeah. Okay. And yeah. And actually, one thing is that say we were trying to compute the connected components of this graph here. I mean, it's clearly connected, but maybe to our MPC algorithm, we don't know that. What we can do is, if we can somehow compute some sort of sparsifier on each connected component, or each region of this graph here, as in, like, for connectivity, you can just replace each connected component with a spanning tree, and a spanning tree is planar, right? If you just replace each thing with a spanning tree, you could just solve the problem on a smaller size problem, right? Because the spanning tree will only have vertices that are on the boundary. So in this sense, if you were able to compute a planar separator, then you could just solve the problem on each smaller instance, right? Because we can make those instances as small as we want. And then as a result, we'll also get a smaller graph at the end. And maybe if it's small enough, we can throw everything on one machine and then solve it locally, right? With no communication required. And so essentially all we need is a planar separator to defeat this 1 versus 2 cycle conjecture. And the slight issue is that we don't know how to find these separators in order 1 MPC rounds. So there's a chunk of the work that will be about finding something that sort of behaves like these separators, but the bounds will not be as good. Yeah. If you're curious, the existing algorithms to construct this, in the normal models of computation, they require BFS and DFS, or I guess BFS typically, and you can't really do that in parallel very easily. All right. So let's look at the framework of Holm and Tětek and how they do it. And so the big idea, like I mentioned before, is they're going to essentially come up with something that is essentially this separator that is computable in parallel. And on each part, they're going to compute a sketch, and then they're going to solve it. So they're going to construct a weak version of the planar separator, and then they solve each part directly, and then they combine everything and then just solve it directly. So what does that look like in a picture form? I'll also get a little bit into the details of how they construct the separator. Okay, so we're given this graph. It's on multiple machines in the MPC model. What we can do easily is we can just sample a subset of edges, right? Because, yeah, if we can sample as large of a subset as we want, but maybe we can just sample a subset that we can fit onto one machine, and then all the machines will send the edges that they sampled into this one local machine. And on this one local machine, they can compute this vertical decomposition, which is just you take every endpoint and you just extend it vertically until you hit something else. And if you look at all the edges that intersect one, what I'll call a trapezoid, because it's bounded by two vertical sides and up to two non-vertical things on the top and the bottom, you're going to actually, you can do this in such a way that you have approximately n over r edges per trapezoid. Okay. And the idea is that if you had, say, a list of numbers and you just sampled your numbers randomly, uniformly randomly, you would expect that if you sampled r numbers uniformly randomly, say, you would expect that in between any two numbers, there's going to be approximately n over r numbers that you picked, right? You can make this stronger. You can make it a little bit stronger in that you guarantee there's at most n over r edges per trapezoid, in the same way that, you know, if you sample regularly spaced intervals, you can guarantee that there's exactly n over r numbers per interval. Yeah. So in this way, this is sort of like evenly decomposing the space, so each part of the space has the same number of edges. And once we've done this, we can construct an auxiliary graph on top of this. So we can choose this r to be as small as we want. So we can choose r to fit on one machine. And so we can construct this auxiliary graph that will also fit on one machine. And this graph will be constructed by just putting a node in every face of this cutting. So every face of the trapezoid, and then connecting it to all the neighbors, and then also connecting the boundary together too. And so in this resulting graph, this is a planar graph that fits on one machine. We can, of size order r, we can now apply the S division theorem. So we can now break the graph, this graph, into regions such that each region has a small number of things on the boundary. It has only square root s vertices on the boundary, and only s vertices inside each region. And for technical reasons, there's going to be there might be some holes, but that's okay. All right. And we're going to really exploit the fact that there are fewer vertices on the boundary than there are inside. And that's where we'll be able to gain something, right? That's where we'll be able to, say, sparsify in some way. Yeah. If you lift it back up to the original graph, because of the way we constructed this, we used this cutting, we can now look at this separator as a cycle or as a connected curve in the original graph. And so in the original graph, what happens is, well, each vertex here corresponded to a trapezoid, right? And so each vertex means that there are some number of edges inside. So we're going to cut up our space into regions such that each region has a lot of edges inside, but only very few edges crossing the boundary. Right? And this is exactly what it means. This is exactly the property of the separator that we needed. We needed some decomposition of the graph such that the boundary had fewer things going on than the things inside. And because we have this, we can now compute some sort of sparsifier in each region. So we can compute it so that it's exactly just a function of the boundary. So for example, the running example will be to compute connected components. If we want to compute connected components, we can replace, if you look locally at this piece, you can't tell whether this is one or two components because they could be somehow connected outside the piece. But if you replaced each piece, the local connectivity with, say, a star, and put it all together, then this preserves the connectivity of everything, right? So now this graph, you're also guaranteed to be smaller by a small factor of square root s. And because it's smaller by a factor of square root s, if you could just store this all on one machine, then you'd be done, right? Does anyone have any questions on this? Yeah. All right. If there's no questions, that's good. I won't go through the actual optimization of the parameters, but you could, you need to pick R. You have to balance some things around, and it turns out you need space at least 3/4, and you can improve slightly to 2/3 by using some recursion. But that's the Holm and Tětek result. And I would like to talk a bit about our result. And let me just mention the idea for the improvement is that we can also use recursion as well, right? Because you saw that in this, if you saw that in this example, the resulting graph is actually a planar graph. So the idea is, well, why don't we just recurse? Because if it's a planar graph, we can do the same algorithm, even if we had really little space. So we're going to, again, also construct some weak version of this planar separator. And we're going to solve, instead of solving directly, we're going to solve it recursively for each piece, whatever solving means. But when we do that, we're going to get some residual stuff. Like in the connected components example, we got two components, but we don't know how they're connected outside. So we need to somehow put the residual components back together. And importantly, we actually need it to put it back together so that it's another planar graph, so we can do recursion. Actually, an embedded planar graph. So we actually need to know an embedding of the graph. And then we can just repeat this process on this smaller graph. Right? So yeah. But the biggest problem, though, is how do we go from the picture on the left to the picture on the right? So if you had this as a subproblem, if you had one machine that could see all of this, okay, great. You can just do whatever local computation you want, and then you can output this graph on the right. But we're not going to exactly be able to do that. This problem that we have is going to end up being far too big, right? We can actually only compute this weak sort of separator for a very small parameter of R. So we can only choose a small enough parameter that all the computation of the separator fits on one machine. So we're actually going to get these gigantic pieces that don't fit on one machine, but we can delegate some number of machines to solve. And so it's not entirely clear how we go from the picture on the left to the picture on the right when you have multiple machines that's doing the computation, and we want this explicit embedding of the planar graph. But one thing that we can do is, well, we can just apply the same algorithm again, right? We can find another form of this weak separator, recurse again, and then we'll get some graph with slightly fewer edges. And then if you repeat this enough times, then maybe eventually you'll get a picture that looks like something on the right. Or much smaller, and the smallness will approach the thing on the right. And so that's how we do that. And then once we do this for every component in the recursion, since we can do each component in parallel, of course, now we can just do this process again, compute another separator, sparsify recursively again, and then now get an even smaller graph. right? Okay, and then that's sort of exactly the entire algorithm. So the technical detail is that you need to, we can only afford to set this parameter to be really small to fit everything on one machine, and you have to pick S to be even smaller. So at the end of your separator, if you apply one step of this separator, you're going to get a very small number of regions, let's say n to the delta over 3. You're going to get lots of edges in each region, n to the 1 minus delta over 3. And you'll get slightly fewer edges on the boundary. And as I said, we're going to recursively redraw each region to get something proportional to the size of the boundary. And so if we do this for every region, right, we will get a graph that's the size of the edges on the boundary for each region. So we'll get a graph with slightly fewer edges. And we'll always assume delta is a constant. So if you just repeat this enough times, the graph is so small it fits on one machine, and then you can just solve the whole thing. Yeah. Right. And so that's the entire algorithm. The only issue is that there are a lot of technical challenges with the gluing step and with the drawing step, right? Because we need these explicit representations of planar graphs. Yeah. So yeah, the number of boundary edges is large, so we're actually going to need to return solutions on multiple machines. And in the base case, this is also something to consider, but in the base case, we'll just use graph drawing. And there are lots of well-known graph drawing results that, if you're given a planar graph, you can draw it in the plane in, say, an n by n grid. So you can embed all the vertices in integer coordinates that are at most n, if your graph has n vertices. And so in the base case, we can use graph drawing, but we're going to need to glue things together, so there might be precision issues, but I won't get too much into that. The biggest technical issue is that our regions are actually somewhat complex. Because of the way we computed these separators, each region could be a rather complicated polygon with n to the delta over 3 sides, and it could have some number of holes. And even if it doesn't have any holes, if you wanted to, say, compute a spanning tree, and you wanted to just connect these two vertices together, and this was the shape of your polygonal region that you wanted to restrict yourself to, if you wanted to connect these 2 points together, you might need to go all the way around the polygon just to get to the other point. And if you do that directly, you're going to need to add some bends to your line. And adding bends is okay, right? But adding bends that n to the delta over 3 bends is not okay. Because if you need to pay an extra factor of n to the delta over 3, then your resulting graph that you get might not be any smaller, right? If you started with a graph that had order n edges, if you had to add this many bends, if you do the calculation, you'll end up with a graph that's also order n. So that doesn't actually sparsify, or yeah, it doesn't reduce the size of your graph at all. So that's very bad. The way around this that we take is, if you look at this graph here, topologically this graph is very simple. There's only one connected component, right? So why don't we just draw this in a triangle with triangular holes, if there's some holes. So the boundary could be complex, but we can choose whatever drawing that we want to output. And we'll choose one with a triangular boundary. And one advantage is if you have 2 triangular boundaries, with the same number of holes. There's something called a compatible triangulation that lets you map between the two triangular regions. So you can add some Steiner points in your triangulation. And what that means is if you wanted to say, and so this, you can map one triangle in one to the exact same triangle in the other. These are some examples. But what that means is, say, if you wanted to draw this graph in blue onto the right triangulation, and you wanted to connect these 2 points, then you can identify this point is in this triangle, so this point is in this triangle, the corresponding triangle, same with the other point. And then the line is some line in that triangle, it's some corresponding line in the triangle on the right. And then in this way, you'll construct an edge that's a straight line on the left. On the right, it's a straight line with bends. And the number of bends is going to be proportional to the number of holes, quadratic in the number of holes. But that's OK, right? The number of holes is always constant in our construction. So the number of bends we add will also be constant. Right. So yeah, so it'll be good to keep things as triangles, but we need to join these triangles together. There could be lots of triangles to join together. And then also we need to join everything together in parallel as well, which may not be so easy. For instance, even in this graph here, we need to join an outer triangular region with 2 regions inside that have some non-trivial boundary as well. So we have to join everything in parallel. That's not so easy, but we construct what's called a scaffold graph to help us do that. And I'll just give some high-level ideas from what we do. And I'll start with like how you route between curves in parallel. So suppose you had 2 curves, polygonal curves, and you had some points, P, P prime, P double prime on the bottom, that you wanted to map to the corresponding point on the top, and you wanted to connect everything with straight lines, possibly with bends, right? And maybe you can't just draw the straight line. In this example, you could, but imagine that if the curves look wonky enough, then you can't just connect them with straight lines. What we can do is, if you had a single point in the middle that could see everything, then you could open up a little ball around here and then just go through this ball and then not induce any crossings. And for technical reasons, you might need a triangle. We need a triangle for precision issues, but that's fine. And so we're going to construct a scaffold with these points that can see vertices that we want to map to each other. Right? This is what we need in order to glue our recursive problems together, because we no longer have, we're going to assume everything has a triangular boundary. And so for our scaffold, we're going to have some sort of graph or some sort of regions on the left that we have to connect together. Here I haven't drawn any of the edges. These are just the abstract regions in the plane. And there's going to be edges in between them that we need to figure out how to connect. And so once we've redrawn them, we're going to redraw them in triangular regions with triangular holes, right? And so there's going to be some sort of graph inside each region. And we have to join the boundaries together, like that correspond to the same boundary, edges and vertices. And what you can do is you can look at sort of the critical points in these regions. Like this is sort of a joining of 3 regions, the purple, the green, and the yellow. They all meet at this one point. And then you can identify the corresponding point in this redrawn triangle. And they all correspond to maybe the same point. So maybe you want to draw them together, connect them together with an edge. And if you look in between each region, that would correspond to, say, this subcurve. And for that subcurve, you would want to map points on the boundary here to points on the boundary here. So you would want some sort of point in the middle that can see everything. And so we'll just explicitly add a point in the middle and just connect it to everything so that it can see everything. And this scaffold will have size, and we'll call this the scaffold graph. Because this graph will have size order n to the delta over 3. This is size proportional to the separator that we constructed. And so you can store this all on one machine and draw this scaffold explicitly. And if you just draw this as a planar graph with straight lines, then you can store this all on one machine and then do all this routing in parallel, like I said before. There's some technical issues. Faces aren't triangles, but you can construct scaffolds like this on the inside and the outside to make things triangular. Yeah, but that was all sort of fast and sort of just good to give a taste of what the constructions here look like. But let me say something about applications to problems. In our applications, we show this, we essentially show a sort of meta theorem. If you have some sort of vertex sparsifier that keeps things planar, right? So for spanning tree, you can sparsify to, for connected components, you can sparsify to a spanning tree. For problems involving distances, you can compute what's called a 1 plus epsilon emulator. And so an emulator also preserves planarity and also has size proportional to the boundary. So if you have some sort of planar vertex sparsifier, then you can get an order 1 round MPC algorithm for all these problems here. Yeah, you had a question?
Yeah, what did you mean by vertex sparsifier?
Yeah, so what I mean is you have some graph and that's drawn in some region here, and you could have lots of vertices inside here, right? And some complicated graph, right? And I want to transform this into a graph that has size on the order of terminals on the boundary. Yeah, I mean, you can create some extra points inside if you want, but I want the total size of this graph to be sparse, as in terms of the boundary vertices and not in terms of the total number of vertices. And I also need the requirement that it's planar. That sort of thing, well, you have to carefully do it for different problems. For connected components, you can just replace by spanning tree. If you had a weighted graph and you wanted to preserve distances, so maybe this is 3, 2, 1, 7, whatever, you need to come up with some sort of distances here, and then you want to make sure that you don't distort the distances by too much. And you also need it to be planar. And by recent work of Chang, Kruthgamer, and Tan, they showed that you can construct a 1 plus epsilon distortion sparsifier. So this is distortion, and that's using what they call epsilon emulators. For single shortest path. Yeah, so APSP, SSS, yeah, so you can do APSP with a bit more memory too. Weighted distance is just some sort of shortest path problem. And lastly, I'll mention for the flows and cuts in planar graphs that corresponds to something, to cycles in the dual. And we can solve cycles in the dual approximately using these planar emulators. And we can also use our framework to recursively redraw something like the dual. I won't go into any details there, but we can essentially output some sort of dual and then get a cut, and that is good enough to get flows and cuts as well. Yeah. Yeah. And let me just conclude here. So with some open questions that still remain. So, all my questions will be about this fully scalable regime. One question is, can you do, say, Euclidean MST in higher dimensions? So recently, also at SOTA of this year, there was a constant approximation in log n rounds. And we provide an exact solution in order 1 rounds. And so a natural question is there something in between here for dimensions between 2 and arbitrarily high? Yeah. I think there's also a known 1 plus epsilon approximation in constant rounds in constant dimensions as well that I haven't mentioned here. Approximate diameter and radius is sort of a natural harder problem in graphs that where you output, where if you have a planar graph, you only need to output 1 number, right? The diameter or radius. We don't know how to do this in constant rounds. Exact solutions to distance space problems. I'm not sure if this is even possible in constant rounds in the fully scalable regime, because you can't do any sort of sketching or sparsification like this. Maybe it'd also be interesting to ask questions in geometric intersection graphs, because they also have good separators. And I think it's not even very well understood how to do things like planarity testing or graph drawing when you don't have an embedding to begin with. Of course, you'll need, our results actually imply that you'll probably need log n rounds unless you're going to break the 1 versus 2 cycle conjecture in some way, right? Because when you're not given a graph and you're given either 1 cycle or 2 cycles, if you can draw the graph in order 1 rounds, then you can apply our algorithm and then tell whether it's 1 or 2 cycles. So the exact complexity of planarity testing and graph drawing has not been well studied, and at least in the MPC model. Yes, and thank you for listening. And are there any questions, or? Yeah.
Like a couple of slides ago, you said something about in higher dimensions. I don't know what that I don't understand how 3 dimensions would make sense. Like, how could I?
So I'm asking about Euclidean MST. So this is if you're given a set of points in 3 dimensions. Yeah. What is the minimum spanning tree there?
Okay, and that helps because every graph can be drawn in 3 dimensions.
Right, right, but
the edge distances are the distance.
Yeah, so in Euclidean MST,
Solves it in 2 dimensions.
we solve it in 2 dimensions because you reduce it to a planar graph problem on the Delaunay triangulation, which is some triangulation, some planar triangulation of the points. Yeah.
So the 1 versus 2 cycle conjecture.
Mm-hmm.
Why is that believed to be, why is that a conjecture that's believed?
That's a good question. This is sort of like the simplest problem that they realized that they just couldn't do in constant number of rounds. And
problems where we have a proved lower bound?
yeah, so I think all provable hard lower bounds in this setting are very difficult because we don't know very much from a complexity theory point of view about Nick's class and other sort of parallel models of computation and the relationship between them. And so there is some work that relates these conjectures to other complexity theory conjectures that we also don't know how to solve. So there's some somewhat weak conditional reason to believe this conjecture. Yeah, but I don't think anyone, I think most people working in the field take this conjecture to be granted and prove conditional lower bounds based on this conjecture. And so the best known actually, there was a line of work in the last few years that improve the complexity of, say, even just the connectivity problem down to log d, where d is the diameter of the graph. But it doesn't really help in this extreme case where you have an n vertex cycle, since the diameter is n. Any?
Final question I had was, what about Steiner tree? What is known to compute a minimum cost Steiner tree?
I don't know, because even these very, okay, in the general MPC model and the general graph, this might have been looked at, I'm not sure. But even for these embedded planar graphs, like, we were the first ones to look at these very basic questions. I will say, like, it's probably possible to approximate Steiner trees in log n rounds in general graphs. That would be my guess, but I'm not sure if anyone has looked at it. Yeah. All right.